All right, so if I'm multiplying or adding to get an identity, which is 1 or 0, then how would I remember this? Okay, multiplying by inverse gives you 1. So I'm going to say multiply, or mult period, by the inverse gives you 1. And then adding an inverse gives you guys 0. So then what is this identity word that I speak of, right? Your multiplicative identity and your additive identity. So think about how do you identify, or who do you identify with? It's always yourself. So when you have a multiplicative identity or an additive identity, what you're really doing is saying, okay, what could I multiply or add so I get the same number in return? So in other words, if I want to start with A, what could I multiply to also get A when I'm done? Well, that would be 1. So I'm using that identity that I got as an answer when I did inverse problems. Now I'm using it in an identity property. And then if I want to have A, and I want to add something to get A in return, the only number I can add is 0. If I add 0, I get the same number I started with in return. These I'm also going to clump together. Those two also go together, the two identity properties. So when you identify, you get the same answer in return. So let's say start and end with, I can erase this now since we did that example already. I'm going to erase my little side bubble. So start and end with the same number, or expression sometimes we might do this with. So I have commutative, associative, distributive. I have my 2 inverse properties, I have my 2 identity properties, and then we're going into your, I call them the RST 1, 2, 3. RST is your reflexive property, symmetric property, and transitive property. If you guys know Michael Jackson's ABC 1, 2, 3 song, easy way to remember this. Instead of Michael Jackson's ABC 1, 2, 3, it's easy as 1, 2, 3. If you say 1, 2, 3 RST, I know I sound crazy right now, but I promise it'll help. Reflexive is 1 equation, symmetric is 2 equations, and transitive is 3 equations. So the RST, I'm going to put these together in green. These are my Michael Jackson RST 1, 2, 3 properties. And the reason why I say that is because with reflexive, think about it, a mirror, the reflection you're getting. So if I put A, or I'll continue with A. If I put A in front of the mirror, you're going to get A back. You have one equal sign, one equation. So reflexive deals with one equation. Whatever you put in, you get out. So A gets A. For symmetric, what I'm saying is that if A is equal to B, then B is also equal to A. So for symmetric, I have 2 separate equations. I have an if part and a then part. From geometry, right, you guys called this, the if part was your hypothesis, your then part was your conclusion. You guys called this a conditional statement. The only special piece about this conditional statement is that my first equation is the opposite of my second. I'm saying that if your A is equal to your B, then your B is equal to your A. So for example, if I say A is equal to 5, then 5 would also be equal to A. They'd be the same thing forwards or backwards. And then transitive has 3 separate pieces. That would make it have 3 equations. If A is equal to B and B is equal to C, then I can conclude that if I started with A links to B links to C, then A should also link to C. I saw a car commercial recently that had something kind of like this in it. You guys could pretty much make up any scenario here, but if A is B, B is C, then A is C. So whatever you start with, if it links to a second part, then that second part links to your final part, then you can say that my first part and the final part are really the same, as long as they've all linked together. All right, guys, so last but not least, I just want to mention a quick note about the closure property, and I'm going to put a little star by it. Closure is more what you think of a whole number set. So for example, if I take any real number, does it give me a real number when I add or multiply by another real number? So you could take any one of these numbers that we talked about, so any type of number. So let me take my real numbers. If I take a real number and I multiply it by a real number, do I get another real number? Yes, I do, right? And that would work for any example I choose. If I take an imaginary number, since we were just doing imaginary numbers, if I add one imaginary number to another imaginary number, so for example, if I take, let me go back, I'm going to take my little brain bubble on the side again, so I'll put it in red. Okay, if I take I plus I get 2I. So I also get another imaginary answer. What we would say for closure is we would say imaginary numbers are closed under addition, meaning if I take two imaginary numbers and I add them together, I get another imaginary number as my answer. The interesting part, though, with imaginary numbers is that if I take one imaginary number and I multiply it by another imaginary number, I times I gives me I squared, and I squared is a real number because it's equal to -1. So I could not say that imaginary numbers are closed underneath multiplication because I don't get another imaginary number when I multiply them together. I get a real number because I get -1. So closure means an operation within a number set remains in that number set when you guys get your answer. And that's not true necessarily for every single type of number in our complex number system, but for many it is. So for closure, you have to start with one number set, and we say a number is closed, or we'll say a number set is closed under an operation, so addition, subtraction, multiplication, okay, or division. But usually we just discuss addition and multiplication because then subtraction and division follows. A number set is closed under an operation if the solution is also in that number set. All right? And that is it for our properties today. In that number set, if they squeeze it in over here. There we go. Okay? Those are all of our properties. We're going to practice and use them when you guys come to class next time. So think about the number properties and the number sets, and have a good night.